So now we're going to give a proof of the converse of the part of this theorem that we just did. I guess I called it the A part, so I guess we call this the B part. That is, we're going to prove that if a function satisfies this star condition here, then it's a concave function. So let's start writing that down. Say B, that the star condition implies f is concave. So if we're going to prove that the function's concave, we have to take an arbitrary pair of points in the domain and show that the value of the function at every intermediate point is at least as large as the value of the function at the convex combination of the endpoints. So let's start out by saying let A and B both be in capital X. So capital X, you recall, is the domain of our function. And let's let V be the difference between these two vectors, the B vector minus the A vector. And let's let lambda be between 0 and 1. And we're going to say, as we have done often, that x of lambda is just 1 minus lambda. In this case, we'll call it 1 minus lambda times A plus lambda times B. And that could also be written, of course, as A plus lambda times B minus A, or A plus lambda V. And it's going to turn out that writing x parentheses, lambda parentheses is going to be a little bit messy. So we're actually going to say, let's just write this as z, a lot shorter, a lot quicker. And so what we want to do is, let's fix that. What we want to do is we want to show that f at this intermediate point here is greater than or equal to 1 minus lambda f of A plus lambda f of B. So that's where we're going. That's what we want to do. Now, to do that, we're going to use this star condition here twice. And so we're going to use it once, and then we're going to use it again. But before actually deploying this star condition, let's go over here and draw a diagram of what's going on. We've got a lot of notation up here, and I want to kind of fix in our minds exactly what the picture looks like here. So let's go over here, and let's draw a little diagram here. So this is going to be A, and this is going to be B. And so we know that V here is just the distance. Well, it's not just the distance, it's actually the B vector minus the A vector. And let's say this is Z, which we've said is x of lambda. So we need to work with f of Z, f of A, and f of B. So let's say this is f of a here. Let's say this is f of b, and let's say this is f of z. Now, I'm actually going to switch markers here because this one's things are starting to get a little bit fat here. So let's do one more thing here, and that is let's note that this is 1 minus lambda times v. So lambda brings us from here over to here, and 1 minus lambda is the rest of the way. So this is lambda times v. And so let's draw our function in here. And I'm going to draw the function concave. But of course, our objective here is to start with this condition star, which we're going to use a couple of times, and use that to prove that the function's concave. So we don't really know it's concave, but I'm going to draw it concave because that's where we're going to end up. So I'll draw concave function here. And now let me add one more item, and that's going to be the tangent to this graph at z, or at z f of z, at this point right here. And so let's just point out what this is here. So this is, this point over here is going to be f of a actually, we're not going to need to put that in here. So let me take that off, and whoa, that didn't come off so well, did it? We'll get it off of there. Okay, there we go. I don't think we're going to need that. So let's check and see as we go along here. So we said we're going to use this star condition twice, and so the first time, let's say we're going to say f of z plus, and now to start with, I am going to write this proof for L equals 1. So our domain is just R, much as we did for the A part of the proof. But then, of course, it'll be easy to see how we can fix the proof or generalize the proof so that it works for multidimensional domain. So here we have f of z plus f prime at z times 1 minus lambda times v is greater than or equal to f of b. Now, that is presumably kind of mysterious. Where did I get that from? And so first let me point out that what I'm doing here is I'm writing, for delta x, I'm writing 1 minus lambda v. And let me also go down here. And what I'm going to do down here is I'm going to point out what is playing the role of each of the items in that star condition in inequality 1. And then I'm going to do exactly the same thing for an inequality 2 that we're going to write down. So let's do that down here. And so what I'm going to do here is I'm going to say in star, and then I'm going to say over here in inequality 1, and over here I'm going to say in inequality 2. And so the things I have to identify in the star condition are x bar, x, delta x, and I'm also going to identify gradient f at x bar delta x. So in this first inequality, I want to fit that into the star condition. Okay? So you'll see that the first item in the inequality in this star condition is f of x bar, and I've got z. So z is playing the role of x bar. We have f of x on the right-hand side, and here we have f of b. So b is playing the role of x. Delta x here, we've said, is 1 minus lambda times v. So this is 1 minus lambda times v. And so this is the gradient of f of x times delta x. But of course, I've said we're doing all this for just L equals 1 right here. So that means this gradient is just the derivative. So this is just f prime at z, because z is playing the role of x bar, times, and now this is what's kind of tricky. It's 1 minus lambda times v. So let's write 1 minus lambda times v. And now let's go back over to our diagram over here and see how all this is working out in the diagram. So again, what's going on is we're applying the condition star. And so the way I'm applying it is to say that this z is playing the role of x bar. And so what I'm doing is saying that I'm applying star in this direction from z, as if it was x bar. And so the delta x, the change that takes place in the x variable from z over to b, is not all of v, it's just this part right here, 1 minus lambda times v. And so I know that this point over here is f of z, the height here, plus the derivative of f at z times delta x, the amount of change in x, which is 1 minus lambda times v. So that is completely straightforward, I think. You know, we're using the derivative at z. That gives us the slope of this orange line. And we know that this point here, then, the value of f is going to be the value it was here, plus however much it changed as we went out here. Now notice that's exactly what we have here. Here it's in pink, here it's in green, but they're the same. So this is the condition star applied in this way, applied to this situation from here over to here. And now we're going to do exactly the same thing, going from here over to here, this direction. So in fact, I might as well put that in here first before we write out the, it's supposed to be a little arrow there. It's not much of an arrow. There we go, it's a little better. And so what's happening here is I want to find out what the value is here. And so let's just maybe do this, okay? And by analogy with this, or applying this star condition, in fact, let me put those things in over here. Let's put z here. Let's say this is going to be a now, and this is going to be lambda times v, but it's going to be minus lambda times v because I'm going that way, not this way. So this is minus lambda v, and so this is f prime at z times minus lambda v. So coming back over here, then doing the same thing we did here, we have f of z, value here, plus the derivative of f at z, telling me the slope of the orange line, times the movement away from z to get to a, which is minus lambda v. So now we're going to just write this in over here. So we have f of z plus f prime of z times minus lambda v is greater than or equal to f of a. And let me do the same thing here. Here, delta x is minus lambda v. And now, notice one other thing that I perhaps should have already mentioned, and that is the inequality. That is that indeed it's the case that the height here, this level here, is above f of b. And of course it's strictly above because I've drawn the function strictly concave. But the function's concave, so I know that it's at least as high as this. And that's what this says. This expression here is this expression, that's the height here, and that's at least as large as f of b. Same thing down here, this expression is at least as large as f of a because the function's bending downwards in this direction. It's concave. So it's this kind of picture that Starr is describing, except that we don't know the function is actually concave. It could be wiggling around, could be going up and down in here, but that's just because I've picked a particular lambda, particular z. But if I do the same thing at all the z's across here, then I get a guarantee that the function will actually be concave, and that's what we're going to do here. We're going to say now it's just basically one more step to complete the proof. What we're going to do, and I'm going to put this in quotation marks because it's just a sort of a kind of a little description. I'm going to take lambda times the first inequality, and so that I'll just say 1, so it's inequality 1, and I'm going to add that to 1 minus lambda times the second inequality. Okay, so that looks a little odd because that's not something we normally write, but let's just carry it out and see how it works. So I'm going to take lambda times the left-hand side here and lambda times the right-hand side, preserving the inequality. I'm going to take 1 minus lambda times this and 1 minus lambda times this, preserving the inequality, and I'm going to add the two left-hand sides, add the two right-hand sides, again, preserving the inequality. So let's just carry that out, and let's give ourselves a little room here. So lambda times this is lambda f of z, and now I'm going to add this part, and that's going to be 1 minus lambda times f of z. And now I'm going to add these two parts, so I have f prime at z times lambda times 1 minus lambda times v. Now I'm going to add this part, which is 1 minus lambda times minus lambda v. So I have minus lambda v. Let's make this lambda 1 minus lambda times v. And now on the right-hand side, I have greater than or equal to, and I'm not sure I can squeeze all this in, so I'll write it this way. 1 minus lambda f of a plus lambda f of b. Okay, so that's what I meant by this little funny expression here in quotation marks, is that I'm taking lambda times this, 1 minus lambda times this, adding them together, lambda times this, 1 minus lambda times this, adding them together, preserving the inequality. So I still have the inequality. So now let's note that this lambda plus 1 minus lambda times f of z is just f of z. And this in the square brackets is 0, because I've got lambda 1 minus lambda v minus lambda 1 minus lambda v, so that's 0. So now what have I got? This inequality says f of z is greater than or equal to 1 minus lambda f of a, there should be a right parentheses on that, plus lambda times f of b. But what was it I was trying to prove? That z, sorry, this is what we're trying to prove here. We're trying to prove that f of z is greater than or equal to 1 minus lambda f of a plus lambda f of b, which is exactly this. f of z, greater than or equal to 1 minus lambda f of a plus lambda f of b. So we just completed the proof. That's it. So this gives us now the other half of this characterization theorem, which tells us a condition star that is both necessary and sufficient for f to be concave. Whoa, there's one more thing that we have to do here that I almost forgot, and that is that we just did the proof here for L equals 1, and this is supposed to be for RL more generally. Here they have the picture where we just had the domain was just the real line, just the reals. So all we have to do to change what we wrote in the proof is just to change the three places where we have the derivative of f at z with the gradient of f evaluated at z. So we just have to replace the derivative in each place with the gradient. So in effect, all we're doing is taking out the little prime and sticking on the upside down delta. And that's all we have to do in the proof to convert the proof into a proof for general L. And of course, we're now interpreting x, x bar, and v now as vectors as we were at the beginning, rather than as just numbers like in the picture down here. So now we do have the complete proof of this characterization theorem that tells us that the function f is concave if and only if the star condition is satisfied. And now the next thing I think we want to do is look at this corollary. So the corollary here is an immediate consequence of the theorem. So the corollary says if we've got a concave function f and its gradient at x bar is the 0 vector, then x bar is a global maximizer. In other words, it simply says that for a concave function, having the gradient at a point x bar be the 0 vector is a sufficient condition to ensure that x bar is a global maximum of the function. And of course, that comes immediately from the theorem, because if the gradient at x bar is the 0 vector, then in the left-hand side of our inequality here, we have the two terms, f of x bar and then the gradient times delta x. And the second term, gradient times delta x, that's all 0 if the gradient's 0. So the star condition becomes that for, and of course the x bar is now fixed here. We've got a particular candidate x bar to be a maximum. And so now the star condition says that for any vector x in the domain, f of x bar is greater than or equal to f of x, which means exactly that x bar is a global maximum of f. So this corollary is just a trivial, direct, immediate consequence of the theorem. Now, I think we want to say a few words about the theorem and how we use it. You know, what part of the theorem is more important, and so on. So the theorem is a characterization. So it says that f's concave if and only if the star condition holds everywhere in the domain. Now, it's both sufficient then, so the star condition is both sufficient condition and necessary condition for f to be concave, but we don't really use the sufficient condition very much. And the reason is, I think you could kind of guess this yourself, it could be a little difficult. In fact, it is generally difficult to verify the inequality in the star condition, to verify that the inequality actually holds for every pair of points in the domain. We can't go around checking every pair of points. And so it's actually not straightforward. It's actually typically kind of difficult to verify the inequality at all the different pairs of points in the domain. So several things kind of come from that. One is that we mostly use the theorem as a necessary condition. If f is concave, then it has to satisfy the star condition for any 2 points. And so we already saw how we can use that in the corollary. The corollary used that exactly. This actually raises the question, how are we going to go about ensuring or verifying that the function f is concave in the first place if we aren't able, or it's too difficult, to use this star condition as a sufficient condition to say that f is concave? So how are we going to verify that f is concave? And the answer to that is going to be that we also, in addition to this first order characterization theorem for concavity, we have a second order characterization theorem for concavity. And I'm going to now stop for a moment to erase our picture down here so that we have some additional space to put that second degree characterization theorem here on the same screen with the first degree theorem. So we'll just pause for a moment while I erase this, and then we'll be back and we'll look at that second degree, that second order characterization theorem. Okay, so now we have a little bit of space down here where we can put that second order characterization theorem. But what I'm actually going to do is I'm going to take off the part at the top that says this is characterization theorems, and I'm going to move everything up on the screen a little bit to give me a little more space to put yet another corollary down here below. So let's do that. And so here's the first order theorem that we just did. Here's that corollary that we just did. And so here is our second order, our second derivative characterization theorem for concave function. So notice what it says. It says that x, of course, is the domain of the function, and it says here we're going to assume that it's an open set and that the function f is C2. It just means, of course, that it's all the second partial derivatives exist and they're continuous functions on the domain. So it's C2 everywhere in the domain. And so the theorem has these two parts. Let's ignore the B part for the moment. Let's just focus on the A part. So the A part is a characterization theorem for concave functions. It says that a function's concave if and only if the Hessian matrix of its second partial derivatives is negative semi-definite everywhere in the domain. That's an important additional point, everywhere in the domain. So it's a characterization theorem. So that means in particular that having the Hessian matrix be negative semi-definite everywhere is sufficient to guarantee concavity. And so that then tells us that f is concave, and then we can use the condition star, which is a necessary condition for concavity, for example, to get this corollary or to infer other results that come from this star condition. So that just shows kind of how we go about getting sufficient conditions for the function to be concave. But of course you could say, well, that raises the same question again, is how easy or difficult is it going to be to verify that the Hessian matrix is negative semi-definite everywhere in the domain, which is what we're going to need to do if that's going to be a sufficient condition for function f to be concave. But of course, that's something we've already done, because the Hessian matrix, the symmetric matrix, second partial derivatives, and when we were working on quadratic forms, you'll recall that we actually worked out the necessary conditions and, for our purposes here, the sufficient conditions for a quadratic form or its symmetric matrix to be negative semi-definite at any point, and we can use those principal minor conditions across the whole domain typically. And so we actually know how to verify that a Hessian matrix for a function is negative semi-definite. therefore verifying the function's concave, and therefore enabling us to use the theorem up here, and that's what enables us to use this corollary. So it's kind of several steps, but we can just see how necessary conditions or the sufficient conditions play out in the way we use them. Before looking at B, the B part of the theorem here, let me just emphasize again that the A part is a characterization of concave functions in terms of second derivatives. And so now let's go down and look at this next corollary down here. This corollary says that so it looks like the first corollary in one sense. It says if the gradient of f is the zero vector at a particular point x bar, and if the Hessian matrix of second partial derivatives is negative semi-definite at every point in the domain, then those comprise sufficient conditions to guarantee that x bar is a global maximum. So this looks kind of different from what we had done with local maximum, because there we needed to know that the gradient was the zero vector, but we needed to know that the second derivatives, or the matrix of second derivatives, was negative definite. But that was where we were looking at local maximization around or near a specific vector or point x bar. Here, while we're looking at a specific vector like x bar being a global maximum, the condition in terms of the matrix of second partials, h of x, the Hessian matrix, that's a condition that has to be satisfied not just at x bar, that has to be satisfied everywhere in the domain. And that's the trick that makes this corollary, makes this theorem go, actually, is that the matrix is negative semi-definite on the whole domain. So this gives us now a set of sufficient conditions to check to guarantee that a point x bar is a global maximum. We just check the first order conditions, the first derivative condition, make sure the gradient's the zero vector, check the second order conditions, make sure that the matrix of second partials is negative. All we need is semi-definite. If it's definite, all the better. All we need is negative semi-definite on the whole domain. Then our point x bar is a global maximum. So now let's close out by coming back to the theorem and looking at the B part. Now the B part of the theorem is actually not a characterization, because you'll notice it's not if and only if. It says if the Hessian matrix is negative definite at every point in the domain, then f will be strictly concave. And so notice then that that would imply that if we have a global maximum, it will be a unique maximum. And so we could say down in this corollary, we could alter the sufficient condition just a little bit to say that if the gradient of the function at x bar is the zero vector, and if the Hessian matrix is negative definite at every point in the domain, then the point x bar is a unique global maximum. I guess the last two things I want to say are, number one, I'm not going to do the proofs of the A and the B parts of this. I'll refer you in the lecture notes to a place where you can see the proofs if you're interested, but we're not going to do them here in the lecture. And I guess the last thing I'd say is that the B part of the theorem, I've just pointed out, it's not a characterization theorem, because it doesn't say that if f is strictly concave, then the Hessian matrix has to be negative definite. And it's easy to see a simple counterexample that shows that that would not work. Let's just suppose that we're in R1. So the matrix of second partials is just the second derivative. So let's just suppose that we have we have the function f from r into r, which is f of x is, let's say, minus x to the fourth, for example. So for that function, we have f prime at x bar equals f double prime at x bar equals 0 if x bar is 0. And so this function is strictly concave, but its second derivative is not negative definite, although it's only a number. So negative definite here just means negative. So here we have a function that's strictly concave, but its second derivative is not negative. So counterexample, simple counterexample showing that the B part of the theorem doesn't go the other way. So it's not a characterization. All we get here is a sufficient condition for strict concavity. So I think that is pretty much everything that we need to do today concerning global maximization, its relation to local maximization, the first order and second order conditions for ensuring that we have a maximum, or the necessary conditions that flow from that, and the relation of those two functions being concave. So I think that's it for today. See you all next time.